Okay, let me start. Thanks for coming to my talk today. My name is Koji Noguchi from Yahoo, and my talk is about a collection of small tips on further stabilizing your Hadoop cluster. So this is my agenda for today. I'll talk about who I am and what's not going to be covered in this talk, and then share some of the things that I found useful, and followed by the Q&A. So who I am. Depending on who asks, I say grid solutions or grid support. But mainly I do is user support for people who's using internal Hadoop clusters. And I work with our ops and dev closely. So I wish I can say I cover everything, right? But in reality, what I'm doing is I'm picking up those tiny pieces that none of the user ops or dev are picking. So based on that, today's talk is not going to be about how ops do the automation on break fixing, upgrading, monitoring, nor about how dev configure the clusters efficiently. And I'm not going to be talking about how users use Hadoop clusters or how they tune their jobs. Instead, I'll be sharing you some of those tiny things that I tried. And most of them were useless, but some turned out to be more useful than I initially thought, and which is including identifying slow nodes, misconfigured nodes, CPU wasting jobs, HDFS wasting users, and queue congestions. And I'll be spending probably like half of the time on this, the first two, so figuring out which one is slow or finding out which one is the misconfigured nodes. These two changed how I interact with the users and how I start debugging issues. So if I say, OK, slow nodes is a problem for Hadoop clusters, you may wonder, OK, Hadoop is known to be great in fault tolerance. What's wrong with it, right? So if the node is having a complete failure, oh, could you start the timer? If the complete failure, then it's great. It recovers very fast. But if the node has having trouble being slow or having partial failures, then it's not so great. If you run some large jobs on Hadoop clusters, you've seen some of the tasks get stuck in one of those slow nodes. Right? So task schedule on the slow nodes can take forever. And you probably also know that there's a feature called speculative execution. Right? When the resource manager or the job tracker, basically the central server says, OK, if the task scheduled on this node A seems slow, then it creates a complete copy, same executable with same input and expecting exact same output, and then let it compete. Right? That's speculative execution. And then the central scheduler would take the output from whichever task that finishes faster. This works mainly in most cases, but one case is that what happens if node A and node B is slow? Right? You're stuck. Both of the tasks will be slow. The other more subtle thing is HDFS itself. Right? HDFS consists of a file. Each file has a block, and each block consists of 3 replicas, usually. If these tasks are reading from the same replica, which exists on node X, and if this node X turns out to be slow, then both of your original task and speculative task that schedule on the 2 different nodes will be also slow. So in reality, the speculative execution helps a lot. It works. But both nodes could be slow, or you could be reading from the same slow data node. Or in some cases, not all jobs. Like if I have users telling me that, OK, I cannot run speculative execution because I have some external dependency, like having connection to the database or having a network doesn't want to consume so much network outside the cluster. So if this is a problem, then how does it used to work? Before I was able to detect it automatically, I'm kind of ashamed to admit myself, but if you have hundreds of users on the cluster, then there's always 1 or 2 great users that's giving me feedback. Right? They would say, OK, my job is slow, or there is a slow node even. And I take a look at it. I report to ops. Ops take it out. And then things will run fine for a couple of months, 6 months, and then comes back. Right? It's not ideal, but at least it was working. or at least it seems like it was working. Until what happened was automation. Right? What ops started doing was, instead of manually configuring the nodes, they started scripting everything, right? So that you can maintain more nodes per ops, or you have less number of nodes being forgotten or being stale. Everything was good, except that this loop of a couple of months became 1 day or even a couple of hours. So now this great user, he's going to be unhappy, right? He's going to be yelling at me saying, OK, Koji, you said you took out this slow node, but the next day he has the exact same problem. And if I go to ops, ops would tell me, OK, it's passing the load test. So for them, they cannot stop adding back nodes. Right? They have to keep on adding nodes so that the number of down nodes are not too many. And if I go to dev, they will tell me that, oh, we're not supposed to be adding those slow nodes. Right? So I'm stuck in the middle while my users are yelling at me. So I needed a way to detect, instead of relying on the users, detect the slow nodes myself or by the script. So finding a good place is like, OK, in this case, OK, finding which road is better, rocky road or highway. And if I want to run a performance test, I would never going to be running supercar on the left-hand side and the superhuman on the right-hand side, right? The performance test means nothing to me. You want the exact same car, exact same engine, exact same driver, and so forth. An equivalent of this in MapReduce is you want the same executable code, you want the exact same input, and you want the exact same output. And that's equivalent to what I said before, speculative execution, right? So in the slides before, when I said speculative execution, was because was about users using this feature to overcome the slow nodes problem so that their jobs would keep on running. Here, I'm talking about speculative execution using those logs and statistics after they have been run, and then maybe after 1 day or after a couple of hours, and then using those logs to identify these slow nodes. So in order to do that, this is the same graph, same diagram, but on the x-axis, I have time on it. So at time 0, this original task starts at node A. Scheduler says, OK, it's too slow. Schedule a speculative task on node B at time 10. And this speculative task on node B turns out to be much faster than the original task, and it finishes. So if I see this in the log, what I first did was, OK, I start counting how many times this node A lost. But if you think about it, this node A could be slow, or it could be the source node, node X, that is providing the input to this node A, could be slow as well. However, to take out these false positives, I also start doing, OK, how many times did this node B won, right? On this node B, speculative task started the task much later than the original task and finished much faster than the original task. So it tells me something about this node B being very good. So there's not much scientific in this, but it's just counting. So to do this, there is a job history log. And in the job history log, you have all the necessary information: attempt ID, start time, finish time, where you ran, and status, and how long it took, actually, basically. Within Yahoo, what we do is we mine these logs, and then we run a query on top of it. However, there's nothing stopping you from directly reading this job history log yourself. And this is a big query that I wrote. I don't want to go over it. However, the summary is this. The first 2 lines is I try to find any tasks that has the first attempt killed and second attempt successful. And the first attempt turns out finishes later than the attempt, the speculative next attempt, meaning the first 2 lines identify the speculative task. And then I just give win count and lose count on 1 each. And I agree per node. And I list all the nodes that lost, in this case, I lost 4 times more than E1. That's a way to say, okay, this is probably something wrong with this node. But also, I have another condition saying, okay, it lost more than 50 times. This number is random, but I wanted to exclude the case where the cluster is completely idle and not being used that much. In that case, I don't want to list those nodes because I don't have enough counters or stats to be reliable on. So with this, let me go with the second bullet. When I listed, what I didn't expect was I started seeing a trend. Right? Our cluster was mixed with 24 gig memory node, 48 gig memory node, 64 gig memory node with different number of CPU. I started seeing a trend on one type of nodes were much slower than others. And obviously, I didn't want to take all of those one type of nodes. So what I ended up doing was, instead of looking at the failure nodes, I saw that all the slow nodes that I was interested in the first place, it never won. Or it won like, okay, 1 or 2 times against the original task. So I started taking out nodes if that node turns out to be failing, losing 50 times, winning 0 times, 2 days in a row. The reason I'm being overly careful is I don't want to give false positive to the ops too many, in that case where they would start stopping, they would stop trusting my outputs. Right? So this graph shows, okay, I started doing this in 2013 January, and the red one shows the new nodes that I reported to them, and the blue one node shows the one, any nodes that was previously reported. So we have ops somehow we added back those slow nodes. So with this, I was kind of surprised to see that, okay, I thought this model of relying on the users was working for me. But when I started running this script, like a bunch of slow nodes that I looked at before start showing up. So, which gave me a confidence that, okay, this is sort of working. In total, I think I reported about less than 100. So it's about like 0.2 to 0.3% of the entire cluster that turns out to be slow. Sometimes ops add it back, and it turns out okay. So the second one issue that I have is misconfigured nodes. If a node that tasks repeatedly fail for some users or some jobs, but not for all the users. Right? And it's like termites to me, because when user comes to me and say, okay, my job somehow failed on these 4 nodes, is it misconfigured? If I get the kind of question, there's definitely more than 4 nodes that's misconfigured. Right? If user notices some misconfiguration on the node, it's already too late. I want to find it before the user notices. So this is the original condition that I had for the speculative task. First attempt killed, second attempt successful, with some time condition. I just changed it simply by saying, okay, any task that first attempt failed and second attempt successful, and then aggregate by the node. And I list any node that had, okay, 30 failures per day, and then I list a couple of attempt IDs so that I have a link to jobs. So that if the error message is not good enough to debug, I go to the user log and see what I can find. These simple things, I wasn't expecting much, but it gave me so much information. First, it started showing me, okay, which nodes were misconfigured, missing the Java library, missing some files that was supposed to be there. Or detected regression when we were doing OS warning upgrades. We were telling users that everything will be transparent when we upgrade from one OS to another OS. But when we started doing the OS upgrades, we saw that some tasks start failing on those nodes. Right? And what was good about this was it's not like users complaining to me. Instead, I was able to find that issue and reach out to the user saying, OK, your job is failing with these OSs. Can you fix it as soon as possible? Or should we stop this warning upgrades so that eventually your job would start failing if we don't do anything? The other things I started seeing was some OS-specific regression errors that was mysteriously happening, like make their failing on certain subdirectories, or user lookup failing for some users, but not the other users, which was weird, but having this data and give stats to show to dev, it helped us figure out what was happening before it became a real issue. And the third one was partial network error. I thought my initial slow node detection script would catch all the cases, but what was happening was when the nodes are failing on localization, then speculative execution doesn't kick in. So I needed this extra check to say, OK, something's wrong with these nodes when localization keeps on failing with 10-minute timeouts. Or if I see map fetch failures showing up on specific subset of nodes for like a couple of days, I know for sure that, OK, probably these nodes are reachable from one node, but not able to communicate among those map fetching failure nodes. And last one was, it also helped detect Hadoop bug in that there's one feature called disk fade in place, where if the disk becomes read-only, you take out those disks, but you still keep on running. But what was happening was on those nodes, we started seeing class not found errors. And it turns out that there was some inconsistency between how the node manager or the task tracker have in cache versus what kind of jars were stored in disk. So all those things started popping up. And what was good for me is, again, instead of waiting for users to complain, we started reaching out to users with tickets, saying, OK, these are breaking for you. So those are the two main things I wanted to cover. The next one is little, not that important compared to the two, especially because with Hadoop 2.x, you have CPU-based aware scheduling, and everything going to change. And we are still running 0.23 on most clusters. So in 23, with capacity scheduler, it's based on memory, and the limitation is enforced for memory, but not for CPU. So if you have a cluster with 80% CPU utilization, 90% CPU utilization, you would have some nodes that is like extremely slow. So what I wanted to catch was, OK, which job is making that load? So there's a counter called CPU time spent, or GC time spent. So using these counters, and also these are available in job history, I start gathering the time is spent on CPU divided by the time this attempt ran, or the time is spent on GC divided by the attempt time it ran. The GC time is elapsed time versus CPU time is aggregated. And then I started getting the max and average. And it was important for me to get the max because even if you have a job with 100 reducers and 99 reducers are running fine, I wanted to find if that one remaining reducer is like eating 20 CPU threads. I want to know that. So by that, I was able to gather the data and show the users, OK, this job is taking 10 to 20 times of the CPU. This job is having a task that's eating like 10, 20 CPU threads and affecting the health of the cluster. And also, sometimes I would be able to say, OK, this job is using 0.1% of the entire cluster capacity, but as a total, you're using 10 times that for the CPU time. Right? Those numbers were helpful for me when I reach out to the users. And what also was interesting for me was there was one case while I was working with a dev. There was one job using 85% of the time on GC. And I asked them, OK, can you move from parallel GC to serial GC? And I was expecting that job to run much slower because what was running parallelly was now moving to serial. But next day, the user came back and said, oh, thanks, Koji, the job runs 3 times faster. I didn't know how to explain it. But there was, I also, again, I asked the developer for help, and they would give me an explanation on probably this job itself was competing to each other within that job. Right? If you have 2 tasks for the same job, eating 20 CPU threads, of course, it will be much, much slower. So it was not only running 3 times faster, the GC times was much lower as well. It was 50%. When we moved to G1, it was a little faster as well. But we initially thought, OK, maybe we should be using this data as an example, move our default GC to 0 GC. But with 2.x coming, everything's going to change. So I don't know what the conclusion would be. But having this data is helpful. The fourth one is HDFS wasting users. When I first started supporting the clusters, like 7, 8 years ago, I always sent an email to the user saying, OK, please delete the data, please delete the data. Right, cluster is full. But after we enforced the quota on the user directory and the project directory, it got better. But still, once in a while, even today, I saw an email saying, HDFS is almost full. Please delete. Right? The problem with this email sending to hundreds of users is, right, nobody listens to me. Right? They would think, OK, other 99 users are going to fix it for us. Right? So I need a way for me to say, OK, I'm talking to you and not you. Right? So each user, I need to target this email. So what I started doing was I started looking for a large directory that is not being changed, the size hasn't changed, or the size has suddenly increased in 1 month or 1 week, or any large directory that hasn't been accessed, or any large directory that is not being compressed. The third thing, it turned out to be a little tricky, and I got worried that user would delete some important data if I push too much, so I skipped doing that. And I'm doing these 3 things periodically. The first 2 things is easy. I just take count, like daily, every day. Right? I know how much data was being used on 1 week ago, 1 month ago, 1 year ago. And then just compare with the amount of data being used today. And then I can say, OK, you're not using the data. The data size hasn't increased, hasn't changed for 6 months. Is this directory stale? Or, OK, we're hitting this space issue, and you increase the size by 100 terabytes in 1 day. Can you delete? Right? If I show this data, and they're likely to comply. I mean, they're very nice users. So by keeping this simple count was helping me a lot. The fourth one was a little tricky because we have petabytes of data, like 10, 20, 30 petabytes of data on the cluster. And I don't want to be reading all the data to say, OK, which one is compressed and which one is not. Right? So one way to say is I can report to the user saying, OK, this user home directory is not compressed. Or I can go to the finer granularity and say, OK, these are the median files that are not compressed. But I don't have much resources, and I don't want to put too much load to the cluster. So what I ended up doing was I got interested in any directory that is uploaded periodically by daily or hourly or something like that. And if I look at the path, they tend to have numbers. Right? And so this is my CD script. I start from the root. I look for any large directory that has some kind of numbers, right? With like more than 6 or 7, it's an arbitrary number. But I look for the directory with some numbers. And then once I find that directory, I take the first 10 megabytes of that directory, of that file, and then try and compress it. And also, when I choose a file, I choose a file that is large and recently uploaded. And I'll explain why I do that. But with that, I get an output like this. I have the directory name, size, in this case, it was 70 terabytes, and cluster name, username. And this compression ratio is not based on compressing the 70 terabytes, but it's based on compressing this 10 megabytes. It's not reliable at all. But it still gives me an idea of there's something going on this directory. And I can go to the user saying, OK, are you compressing all the data? In most cases, it's not. And the reason for looking at the recent file is because as soon as users start compressing the file that they upload, then I'm OK. I don't expect these users to start compressing everything again and then come back to me. So what I'm asking for this case is, please start compressing. And as soon as you start compressing, then my script would not pick up your directory. And eventually, all the old ones will get redented. So with this, by periodically collecting the HDFS usage and compression state, I was able to identify stakeholders, suddenly increasing directories, and also list of directories that are probably not compressed. It's a silly script, but really useful. And the last one is some of the questions that I get from the users, especially for the busy cluster, is, OK, why did my tiny jobs, which used to take a couple of minutes, run for a couple of hours? And my initial answer is, OK, I don't know. But because it's tedious to go back to the logs and figure out, OK, what exactly was the cluster state? And after all, it could be bug in their Hadoop code. But so what I started doing was quite simple. But so if it turns out to be, if it's a queue issue, and if I tell the users, OK, the queue was full, the next question I know that is coming is, OK, why was queue full? Right? And another answer is I have no idea. But so what I started doing was I started capturing the output of MapRed job list. This gives me the list of jobs that's running, as well as amount of resources it's using. This is output from 23, and it's a little different for Hadoop 1, but it's the same idea. Right? Then I start plotting this usage based on the users. So by having this graph, this is for one queue. And then the red line shows the queue capacity. The yellow one shows the queue max capacity. Right? Giving this to the user, now my work is much less because user himself can figure out, OK, if he's a brown user, like here, he would know that, OK, my job was slow because it was already hitting the queue capacity. Or the orange user might be able to find out, OK, my job got slower here because other users, like brown and blue, started using the queue more heavily. Right? So as a result, I have a feedback to the users saying, OK, when the job is hanging, I just give the graph, and the user can tell himself, OK, probably my job is slow because of the queue. And also, he has an idea of whom to blame to, not going through me, which is even better. And by having this MapRed job list outputs raw available to the users, they can always go back and see, OK, which type of jobs was consuming the most consuming the most queue. So those are the things that I covered: identifying slow nodes, misconfigured nodes, CPU wasting jobs, HDFS wasting users, and queue congestion. And this is probably like maintaining your car. Right? Even if your car is running fine, you always want to check your car periodically. And same here, if your cluster is running fine, even if your cluster is running fine, you want to check some of those things so that you are prepared when you get, instead of getting hit by the huge problem at once. With that, it's my talk, and I'd like to open for Q&A. Yes? Oh, thank you. I don't remember what tools I used. Sorry. But my hope is somebody from those companies are listening, and then they would implement it on their package so that individual user would not need to do this. But I don't know if they would do or not. Any other questions? Yes?
Would there be any techniques similar to this to tracking subtle resource leaks in jobs kind of distributed over time, like you were using JVM reuse on a task tracker?
The question is there a way for us to detect the subtle leak when we're using JVM reuse? And honestly, my answer is I don't know. And partly because we don't use JVM reuse on our clusters. But I would guess that once those JVM that is leaking hits some state, it will start fading. Right? If that happens, then my second script will start listing those nodes. Or if that JVM gets slowed due to out of memory, then my first script would pick up. So hopefully it works, but no guarantee. Any other questions? Yes?
You said you weren't going to cover monitoring or the operational alerting piece, but if you have a better diagnosis, some operational alerting monitoring?
So the question is, outside of all this, is there any tips on how we monitor the cluster health? I should bring some ops architect here. But some of the things that I check myself is the name node GC time, GC percentage, or name node error or warn, a number of error logs. Right? If the user starts hitting the HDFS with over quota, failing again and again, usually those numbers shoot up. So I get that. Also, I check for the average sync time of the name node, because when user hits us with this status calls on the name node, the outbound network interface of the name node can get oversaturated. And then that would eventually slow down the average sync time, and I get the alert. So there are certain things that we check, in addition to what ops are doing periodically. Any other questions? Not you, Alan. But yeah, go ahead, Alan. Oh, no questions? OK. Oh, the question is, how many nodes do we have for detection? I think the official number that we give is 30,000 nodes. It's not one cluster. It's like multiple clusters, 35,000 nodes. And probably I reported like 80 or 90 as a slow or misconfigured nodes. Yes?
Do you do cross data center replication or active-active mode, something like that?
The question is, do we do cross-colo replication with active? Active meaning?
Different data center, cross data center.
For usually we ask, that's taken care of at the user level. So as a maintainer, I don't care what the user is doing as long as they're using less than 10, 20 mappers for this CP. However, there was certain case recently where we needed to know how much data is being transferred between Hadoop clusters. And for that, you can use the audit log and the file list result. And I do periodically report that, saying, OK, this user is transferring, transferring 20 terabytes of data from one colo to another colo, and please stop. We do that. But we don't and also, at the same time, we have an upper limit, saying, OK, if user tries to go above that limit, then we immediately kill it at the network level. But I don't know much detail besides that. Sorry. Yes? How do we monitor hardware issue and network issue? One thing is when the ops bring back the node, they have a load testing, right? And some of the testing would not pick up those issues. So what I'm doing was I'm raising my hand saying, OK, I have no idea what's happening. However, I know that tasks are being slow on this node, right? And then giving a stat to the ops and asking them to take a careful look at it. But what's happening is, OK, since my script is not reporting that many nodes, they just take my output and say, OK, decommission this node. So we don't know how many of these nodes are due to CPU, motherboard, network. We don't have the stats. But we know that if we add back these nodes, it's slow again. Yes? Yes? Oh, it's, each color represents one user. Yes, and the question is, okay, what does the color represent? And the answer is, this is one queue having, what, 10 or 20 or so active users, and each user is using up to the queue capacity and so forth. This is based on the capacity scheduler, which schedules a job based on the amount of memory it requests. So the y-axis is just the total of that. Any other questions? Okay, that's it for now. Oh, sorry, one more time. We are using 23, and we are moving to 2.x. Oh, well, some of the cluster is already 2.x, but we'll be moving to 2.x pretty soon for all the clusters. Right, thank you so much for coming.